So first, I will just give you a brief overview of the STRAW project, which is short for Stress at Work. This is a collaboration between JSI and the University of Ghent in Belgium. We are focusing in this project, or I should say we were, because it's officially ended. We were focusing on day-to-day psychosocial stress as opposed to chronic stress, which is very well studied. And for this purpose, we carried out a diary study in two academic institutions. So our aim was detecting stress from physiological and contextual data, but also modeling stress in relation to work environment. So we published a protocol paper in which you can read about how we carried out this study. It's quite detailed, but I will only give you the main features of it here. So we had a couple of different sources of data. We gathered physiological parameters using Empatica E4 wristband. So this wristband measures heart rate and heart rate variability, skin conductivity, skin temperature, and wrist acceleration. For this, I'm using a Python library that we developed at our department to extract the features from this data. Then we used smartphone sensor data. For this purpose, we used a framework called Aware. And this framework helps you gather different types of data from different types of sensors. So we have physical sensors that can measure like acceleration of the phone, ambient light, perhaps ambient air pressure or temperature, and so on. Then we have connectivity sensors. These are, for example, Bluetooth sensors, Wi-Fi. You can also gather location, GPS, but also other types of location, network connectivity, and so on. And finally, we also gathered some data on smartphone usage, in particular, which applications were in foreground, how often they sent notifications, battery usage, then calls and messaging activity, screen usage, whether the phone was actually actively in use. And then the last point here is voice activity, which was another thing that we developed. It's a method to detect human voice from microphone. So that gives you a sense of human presence near the phone. And then the final source of the data, which is very important, were self-reports. So participants answered these types of questionnaires. They are called ecological momentary assessments because they usually ask you about something that's happening right now or has been happening recently. And we trigger these questionnaires every 90 minutes. So they included around 20 questions. You can see two below. So for example, we asked about coffee drinking, which can influence your physiological parameters. But we also asked about, psychological states, such as this right example, which is in Slovenian, but it says how do you feel, and it gives you an adjective. This one is alert, and then you can just answer on a scale from 0 to 4. So we had a lot of these different questionnaires, and from each we selected a couple of items every time, so that the questionnaire was short. But I'm not going through all of these questionnaires because I'm going to focus on a couple of them a bit later on, just to give you an impression that we measured different aspects of stress and also of the work environment. So we had a pilot study in February 2020, but then the main study ran for almost a year, in which we collected the data from 55 participants from two research institutions, University of Ghent and JSI. You can see here some demographic statistics. But most importantly, each participant collected the data for 3 weeks or 15 working days. We didn't gather data over the weekend. So this is approximately the amount of data that we have per participant. Like I said, they answered the questionnaires every 90 minutes during their workday. They had the application running over the whole period of the study. So the smartphone data was collected more or less continuously, while physiological data, we instructed them to wear the wristband as much as possible, which usually meant at least over their working day, but possibly over the whole day. So now I'm moving on to the analysis of this data, and I would like to present you with some considerations of how to actually set up this this whole stress detection problem. So a typical stress recognition system that you might have stumbled upon in the literature is given in this figure. So you can see that it's similar to ours, because I think our experiment design is quite typical of these kinds of studies. So we gather different types of data, and here it says environmental sensors, smart objects, wearables, and so on. We also had these, which represent also different aspects of data, such as physiological data, behavioral data, contextual data, yeah, also some self-reports, I should add. And then you pre-process this data, extract features in a classical machine learning setup, possibly construct some, you know, intermediate features such as activity recognition. Then you join all of these features together and try to detect stress. So the first part of this pipeline is fairly straightforward, and I mentioned we also have different libraries that can help us with that. But I would, in this presentation, I'm focusing on that last part, which is stress detection and what it actually means, or how you can approach it in different ways. So the first question that arose is, what is stress? Like I said, we measured different kinds of things. We asked about emotions, experiences, and so on. And they can all be related to stress, but once you want to model it in a machine learning problem, you need to somehow define it. We call that a target variable. So we have a couple of candidates for this target variable. And I'll show you 3, which I'll also then describe later on how they behave in particular experiments. So the first one is positive and negative affect schedule. I've mentioned this one before. These are just adjectives that describe emotions, and then participants assess if they're feeling this way on a scale from 0 to 4. They're separated into positive emotions. Here's an example, if you're feeling enthusiastic, and negative emotions like irritable. So this is a very commonly used scale in psychology, and especially related to stress. In our literature review, when we reviewed papers on day-to-day stress and similar diary studies, most studies used negative affect as a stress measure. So this is, I would say, a very common definition of stress. We also had the job content questionnaire, which has questions about work organization and job content. So it also had it has a couple of subscales. Job demand has items like, my job required working very hard. Then job control is how you can control your work or your work process. So for example, a statement is, I had a lot of say about what happened on my job. Then the next 2 scales are about social support. In particular, supervisor support. Here's an example. My supervisor paid attention to what I was saying. Or coworker support, and an example would be coworkers helped each other out. And again, participants assessed how this applied in the last 90 minutes on a scale from 0 to 3. So this questionnaire is about job content, and it's usually used to describe the general job that you have, but we used it on a day-to-day basis, meaning that you can also use it to, you know, describe your last 90 minutes, because of course your job also changes from moment to moment. It's not directly measuring stress, but demand and control especially are important for stress, because usually when a job is more demanding, people are under more stress, and vice versa. When they have more control over the work they do, they are less stressed usually. And so demand and control and their ratio are also in the literature often used as measures of stress. And then the final measure that I want to present is stress appraisal measure, which focuses on appraisal, that that is a concept of how you perceive stress, basically. So we measured it in different ways. This one was a bit more tailored to what was actually going on. So first we asked participants, was there a particular event that created tension in you, and how much tension? So tension could be seen as another word for stress. And if participants answered yes, regardless of you know, the degree of tension, we also asked them about two particular appraisal aspects, which are challenge and threat. So challenge, an example of this would be how eager are you to tackle this event, and threat would be an example like, will the outcome of this event be negative? So these two aspects try to somehow describe whether you perceive an experience as stressful, because you might perceive it as a challenge, and then, you know, you might still be under stress, but it sort of activates you, and people exhibit different behaviors, or the coping is different than when they perceive it as a threat. So another option was that there was no stressful event or no particular event, and then we just asked them in general for the last 90 minutes, to what extent did you perceive this overall period as stressful? So here you see we have two different scenarios, because once we're asking about you know, a general period of the last 90 minutes, and then in the second case we're asking about particular event that also occurred at a particular time and it had its duration. So that's also what we asked the participants about. So I've now described multiple options of how to define stress and what our target variable would be, but we can consider not only, you know, the content of the questionnaire, but also how participants answered to these types of questions. And just from this type of exploratory analysis, we can try to hypothesize which of these target variables will be more difficult to predict. So here's the first example. I've plotted here the participant mean over the whole participation period, so about 3 weeks. And I plotted separately the negative effect subscale of the PANAS questionnaire and the positive effect. And you can see that participants usually answered low on the negative effect scale, which is good for them, of course, that they don't usually experience negative emotions, while positive effect has a higher mean overall, like overall the participants, and is also spread a bit more, so it has higher variability and even somewhat normal distribution. So this plot, looking at the distribution of the scores of these two subscales, can hint that negative effect will be probably more difficult to predict. First of all, a dummy predictor will be very good, much better for negative effect, because we can safely assume that, you know, negative effect is around 0. But also it will be more difficult to detect changes in these positive and negative effects. And for this, I can show you the standard deviation. So this plot shows how varied the scores were for each participant for positive and negative effect. So if you look at the very left part of this plot, you can see that there was one participant that had a deviation of negative effect of 0. That means that they always answered the same, you know, they always assessed it the same, the negative effect. So for that particular participant, for example, we can do no better than a dummy predictor, because, yeah, it's just a majority, right? But you can also notice that in general, the standard deviation for negative effect is lower, which was just what I was saying. So negative effect generally in our participants changed or varied less than positive effect. So again, this means that a dummy classifier will be better, and to beat it will be more difficult. So now I want to also compare the two scales of job content questionnaire, so job demand and control. These are quite similar to what we've seen in positive effect, so they have kind of a normal distribution across participants, and they also have, you know, some variability. So standard deviation is still quite small. If you remember, this is on a scale from 0 to 3, so standard deviation of 0.3 is quite low, but still it's better than 0, of course. And then finally, we have stress appraisal measure. When a stressful event occurred, participants also assessed threat and challenge. And these two scales have actually the largest standard deviation of the scales we've seen until now. So you can see that the mean is almost 1. So these two, judging from their distributions, would be the best target variable, because they actually vary day to day, or even, you know, moment to moment. So it makes sense if you want to approach daily stress detection to take a variable like this one. The problem with these two, of course, is that people only answer these questions when they actually said, you know, a stressful event occurred, which was rare, because first they had to identify, okay, this was a stressful event, and only then, you know, they could think about whether they saw it as a threatening or a challenging event. So while this is a good target in terms of its distribution, it also reduces our sample size quite a lot. So this is what I just said, that, you know, proportion of stressful events is low. As you can see, most of the participants had 10 or 20% of the time had a stressful event. So out of all prompts that occurred roughly 5 times a day for 15 days, they had maybe 10 or 20 stressful events. So if we want to detect, if we want to do anything with stressful events, we have quite a low amount of data, but also we can try to just detect this. So if the event was present or not, so a binary classification problem. And in this case, we do have an unbalanced data set, but that's usually not a problem. At least we keep all the data. So the next consideration I want to touch upon is segment of interest length. So what I mean about this is so how long the period we would try to predict stress for is. So participants were asked about stress in a particular moment of time, and the questions also differed in terms of what they were referring to. For example, a fact referred to, this moment. So we asked, how do you feel right now? Whereas some other questions like job content questionnaire refer to the last 90 minutes, basically. So we first approached the problem as day-to-day stress, meaning trying to detect daily changes. So for this, we just averaged participants' answers over the days, and we tried to predict differences in stress between days. But of course, stress can also fluctuate within a day. So another option is to take, shorter segments. For example, 90 minutes, which is the maximum time between two questionnaires, or just the last 30 minutes, for example, because the idea behind this was that when you're answering a questionnaire, probably the last 30 minutes influence your answers the most. And then about the self-reported stressful events here, of course, we also have multiple options because participants reported their duration, but as always, human memory is not perfect, so we can try to guess when this event was actually happening. And finally, I want to say something about prediction type. So I've told you that these scales mostly have multiple values, so from 0 to 3 or 0 to 4. So it would seem that we can approach this problem as a regression problem. This is especially true when we're dealing with daily means, because once we average, the scores over one day, we get something that resembles a continuous variable more, rather than just 4 or 5 discrete values. So that was also our first try, the regression problem, because it's natural, but we can simplify this problem. We can make it ordinal regression. For example, just saying low, medium, and high stress or effect, or whatever we're actually predicting. We can approach it as a classification problem. Again, we can have 3 classes, or we can just approach it as a binary problem. For example, cut the data and split it into low and high stress, or perhaps split it into low, medium, and high, and then exclude medium values, so that we are left with these extreme values of stress. So looking at all of these different considerations, I try to come up with, how an assessment of how difficult this problem is, and for the target variable, judging from their distributions, I guess that negative effect will be the hardest to predict, while stressfulness would be the easiest, especially if you treat it in a binary way, so whether a stressful event occurred or not. And what I did was I set up a machine learning experiment in which I fixed the other dimensions of the problem, so the others that I've talked about and I will also talk about more. And then I also I only looked at different target variables, and you can see the results here. So in the second column, you can see the target variable that I was trying to predict. Discretization means that I approach this as a classification problem, and I split the values into these kinds of classes. So one was between -1 and 0, including 0. So basically just zeros. and then the high negative effect was everything above 0 to 4. For different kinds of target variables, I discretized in different ways, and this is because they have quite different distributions. Like I showed you, negative effect is very often near 0, so it makes sense to you know, treat zeros as low stress and everything else as high stress, while positive effect is more normally distributed. So there are rarely zeros in there, so it makes sense to treat positive effect as low if it's under 2. And similarly for other target variables. And I'm showing here the average F1 score in a leave one subject out validation scheme. And as you can see, the dummy classifier performs quite differently in different cases. So in the next or the final 2 columns, I gave the results of 2 machine learning models, Gaussian naive Bayes and random forest classifier, and I shaded them in, you know, in terms of how better they are from the dummy classifier. Because as you can see, for example, for positive effect, Gaussian naive Bayes is worse than a dummy classifier. And the order in which I ordered these target variables is the same I've just shown in the previous slide. So it's my hypothesis, but looking at these numbers, it seems that I was at least somewhat correct. So indeed, the stressfulness target variable produced the best results. The difference from the dummy classifier was the largest. But then also the stress event, when we're trying to predict its threat, which is a very good measure of stress, also gave, you know, somewhat good results. And we can also see that negative effect is quite difficult to predict. For example, random forest classifier, you know, produced no better than dummy classifier results. The second dimension that I talked about was segment of interest length. So like I said, we can take daily means, or we can exclude night, 90-minute periods before the questionnaire, 30 minutes, or, you know, look at the interval that the participants themselves reported about the stressful event. And I'm showing a similar table here where I always took stressfulness. I focused on this target variable in the rest of the presentation because first of all, it produced the best results out of the first 4, but also we can use it to somewhat compare periods. So yeah, where the segment of interest is a period or a stressful event. So I use different segment lengths from a full day to 16-hour day, 90 minutes, 30 minutes, and then 20 minutes. So for a stressful event, I actually didn't take into account the duration that participants reported, but rather fixed it to 20 minutes. Discretization, again, is different from different periods, and you can see the results. So in general, the shorter the segment, the easier the prediction is. So the best results are again with Gaussian naive Bayes for a short segment, 30-minute one. And I think this makes sense because, like I said, I think that the last 30 minutes before answering the questionnaire had the most impact of, you know, on participants' answers. So it's reasonable that the last 30 minutes are somewhat most related to what they were describing. Stressful event is also kind of good, but yeah, here remember that we are dealing with a smaller sample, much smaller one. And then the final dimension that I talked about was prediction type. So I think it's pretty clear that treating the problem as a regression problem is more difficult than, for example, binary classification problem. And that's also what is shown here. So for the prediction problem, actually the every combination of models that I've seen and target variables produced results that were just as bad as dummy prediction, which is just a constant prediction. So I'm showing here an example of negative root mean squared error for two different models, linear regression and random forest. And you can see that the error is larger than the one that the dummy produces. So this error doesn't really seem too high on a scale from 0 to 4. 0.7, I would argue, is all right, but we cannot say that these are good predictions if the dummy model actually performs better. So the classification prediction type is an easier problem. And here, the first row represents a multi-class classification problem when we have low, medium, and high stress. The second row represents the same discretization, but with medium values removed. And then the final row represents just splitting the values into low and high stress or stressfulness, which is the target variable, and treating it as a binary problem. And you can also see that the more we simplify this classification problem, the better results we obtain. So now I've talked about some conceptual considerations. So here I was actually trying to answer the questions like, what is stress, when does it occur, or when is the period in which we're interested, and also how fine-grained we want to predict it. And these are all more like theoretical considerations. They don't have much to do with the actual modeling, but they do, of course, set up the modeling. So how you approach the data, which variables you take as a target variable, and so on. But then after this, of course, you have the whole machine learning pipeline where you also have a lot of consideration to make. For example, cross-validation technique is something that influences how good results look. And you probably know that doing a leave one subject out cross-validation, which was what I've shown in the previous examples, is harder than, let's say, 5-fold cross-validation. It's harder because in leave one subject out, you train the model on all subjects but one, and then test it on that one, which means you're testing on the data that you've never seen before. And I'll touch upon this particular point a bit later. And again, here you can see that the average F1 score increases in this order. That is kind of, you can predict already these results, but here is the confirmation. Then we also thought about clustering participants. So we thought about making groups of participants depending on their characteristics. These could be different options like their job title, but or gender, for example. But I took baseline job content questionnaire as my clustering variable, because I actually took the ratio between demand and control, and this should give you the general impression of how stressed individuals are in their daily work life. So here I'm showing an example of 4 clusters. Here I wrote K with a question mark because, of course, you can have different options for the number of clusters, but I split participants into 4 groups depending on their demand and control ratio, which is their general stressfulness. And then for each of these 4 groups, I try to predict stressfulness separately and used leave one subject out validation. Then I averaged the F1 score across all clusters, and you can see the results here. So here I thought that clustering might improve the results, but it turned out that it didn't improve them for Gaussian naive Bayes, and also not for random forest classifier if you take into account the dummy classifier. And the question is why? So first of all, like I said, we can try different numbers of clusters, but also the clustering variable might not have been the best one. I could have also used more clustering variables. And then the final thing I want to say is standardization. So in all of these experiments, I standardized features, but not targets. So I could talk about, their absolute values. So features are standardized because they have very different values. Like you saw, we had physiological parameters, connectivity data, and so on. So a large variety of variables with different units and so on. So it does make sense to standardize them. However, for the targets, the questionnaires were kind of similar on scales of 0 to 4 or 0 to 3. So it's not necessary to standardize them. And here I looked at a plot which basically shows how a person is different from the, let's say, average person. And so the average is around 0. In this case, it's normalized to 0, which is shown in the middle of the plot. And then you can see that some people had, this is for a negative effect, I should say, a particular target variable. So some people usually had lower negative effect than the average person, but then there were some others that you can see on the top right that had, much larger negative effect than the average person, even almost 2 points larger. And these small lines that you see give you an impression of how differently a particular participant answered within their study. And this plot shows you that, participants differ between themselves quite more than the results within a participant differ, which means that one participant who is usually stressed usually gives high answers, whereas another one that has low stress usually gives low answers. So for our problem, when we try to detect daily or within day changes, this seems that it's kind of a difficult problem, because especially for a leave one subject out cross validation, because we can, if we wanted to just predict an average value of stress for participant, that would be an easier problem, because the differences between participants account for more than half of the variance. Once we go within the participant, when we're trying to predict day-to-day changes, that's when the problem becomes more difficult. So that's about standardization. And to wrap up, I would just say that depending on how you set up your stress detection problem, so the target variable you choose, the cross-validation techniques, and all of these dimensions that I've talked about, it makes it more or difficult or easier. And this is a problem when you're searching through the literature, because you see different kinds of results. Some are very good, some are not as good, but generally they're all good, of course, because they're published. And when considering these kinds of results, you should always pay attention on how they approach the problem and whether they simplified it to the point where it's quite simple. Thank you.
Thank you, Junoš, for the presentation. Questions, comments?
I have a question, if I may.
Mhm.
Yes, please.
Thanks for the talk, Junoš. First of all, I wanted to ask you, in a couple of places, you report results of the dummy classifier as being 0 in terms of F1 score.
Mhm.
I assume, I mean, obviously either precision or recall is 0 for this to happen.
Yeah.
But do you have any interpretation why this happens or how this even happens? Because I assume that if dummy classifier were to classify into a majority class, you would get at least something non-zero in both cases, perhaps.
Well, but as soon as one is 0, right? Then you get
Yeah.
the F1 score 0, which means that yeah, a particular model might optimize for, let's say, recall, but not for precision. And this was a thing I've observed, that oftentimes, as it's often the case, increasing one sacrifices the others. So I think that's the reason, I would guess.
Okay,
Yeah.
but I mean, both of them are precision and recall are defined as true positives over something, right? So if you have any true positives that are more than 0, I assume, then I mean, both of them would have to be over 0 because let's say you have recall, I don't know, 0.1 or something, and that's computed from true positives that in the, I don't know, denominator, I think. And then this is also for the precision and vice versa. But what changes is at the bottom of the fraction. So you would get something like I don't know, not a number or something if something weird happened at the bottom. It
I
just
mean,
feels,
yeah. So the majority classifier in a lot of cases, or the dummy classifier is in a lot of cases the majority classifier, which for a lot of these target variables is no stress. So as soon as and the dummy classifier would always predict no stress. So for the positive class, the stress class, that would mean a recall of 0, right? Am
yeah.
I wrong? So I think that that's what happens. The majority classifier has a recall of 0, and yeah, I think that makes the F1 score 0.
You have like 2 classes or 4 classes here, or class value?
So in this case, yeah, I didn't specify in this case, but yeah, it was 2 classes always,
Mm-hmm.
except here.
Mm-hmm.
Here, the first row in classification problem had 3 classes, and you can see that the dummy classifier is above 0.
Can I jump in here, because I was
Yeah.
also wondering about the very same thing. So how did you actually decide what's positive and what's negative?
Yeah, so I always treated stress as a positive class, which means that for the positive effect, for example, I turn this around. So high positive effect, I assigned it a 0, and low positive effect, I assigned that a 1. So I try to approach all of these target variables in a same direction. So yeah, in all of these cases, a positive class is stress.
Yeah, I'm not entirely sure what's the best way of treating this, but what I'm observing here, I don't like very much, because these zeros and non-zeros, I mean, the choice of the positive class, I think, affects these numbers too much, and I don't think we want that. Sometimes I think this is solved by simply treating both as positive and then averaging. So, you take first one as the positive and then the other as the positive, and you average. And in that case, you don't get any effect of this choice. Also, I don't know. I mean, dummy F score of a dummy classifier, I think, is somewhat problematic. Dummy classifier is very good when you want to understand accuracy, but for F score, I have some doubts. And so, I mean, in cases where your non-dummy classifier gives bad results, well, I mean, no matter what we compare them to, they're bad. So that's not so problematic to interpret. But in a few cases, you actually get pretty decent results, but still worse than dummy. And in those cases, I'm not really sure how to interpret that.
So for example, this would be an example of 90-minute segments where the dummy classifier is quite good.
Yeah. So I think it would be, I have difficulty really grasping what's happening here. So I think that for a few of those cases, it would be good to take a look at the confusion matrix to really understand what's happening here.
Yeah,
I think there are some cases where the results were even better.
yeah, probably. Yeah. Here I focused on manipulating one dimension. Yeah, and I could look at the confusion matrices, yeah, for a particular case, but yeah, I just looked at one particular number. So the F1 score or the recall, like Gaspar asked, since the stressful class is taken as a positive and it's usually in the minority, that means that the recall will be low because the dummy classifier. On the other hand, the models, they're then optimizing recall usually. But yeah, I agree that this is worth looking into in more detail.
Okay, I'll shut up because David has his hand raised for a while. I may have some more comments later, but yeah, David, go ahead, please.
Yeah, I had a question about these similar things. Now it's more of a comment than question. Junoš, you said that at some point that some of the models are just as good as the dummy, and that's not enough because they have the same this metric of performance, the same value. But still, your model can be. I mean, a model can be much better than the dummy if you can, let's say, extract some knowledge from it, why it makes decisions, if it's explainable. For example, did you check like per subject prediction between those classifiers and dummy classifier, for example?
Yeah, so I mean, you're definitely right. I agree that, just looking at the performance of the model is not enough. And what we would actually like is having, meaningful predictions, not just good ones. So I definitely agree. But I can also add that, in leave one subject out, cross-validation, which is the one that I use the most, and almost all of these results are using this type of validation technique. I observed that for different participants, the performance of the models was wildly different as well. So for some participants, it was quite easy to predict stress, while for the others, it was difficult. And that, ties back to what I was saying, that participants are quite different from each other in terms of stress. And that makes, the averaging of the F1 score in this case even more problematic, because it does not give you the full picture.
Mm-hmm. And another thing that I was wondering is, so at the end we talked about standardization, but in the beginning you mentioned that some participant only answered one value to some questionnaire. Did you try rescaling the answers per each subject? Let's say one subject only answered 2, 3, and 4, and now you rescale that to let's say 1, 3, 5, so that the variance is let's say as close as possible between the subjects.
Yeah. So the standardization of the target variable is exactly that. So it would fix first the mean of all the participants, and also, you know, the standard deviation to 1. And what it would do in effect is sort of squeeze this plot so that it would all be on the same vertical line. And also the little lines would be of the same length, so they would have you know, a standard deviation of 1. So when you do that, you lose all of these between subject differences. So a lot of the variance in your problem is excluded, but you can focus better on, you know, within person variations. So you're right that for a participant that always gives low scores, so the ones on the left side of this plot, you know, we would be able to compare them with the ones that are on the right side of this plot.
Okay. Yes, thank you.
Thank you for your questions. We still have time for one more question.
May I, if nobody else has a question?
Yes, please.
So I'm wondering how come you decided to stop collecting the data?
What do you mean? For participants, you mean?
For participants, yeah.
Yeah, so the data collection process was actually quite extensive, and it required a lot of resources. As you can see here, for 55 participants, we took almost a year. Of course, that was during COVID times, so it's not really representative. But you know, for 3 weeks of data collection, you can kind of compute how long you need for 55 participants, keeping in mind that you can only handle, you know, a certain number of participants at the same time. This was due to, first of all, technical limitations. We only had you know, a limited number of wristbands available, so that limits the concurrent participants, you know, right away. But also the effort that they require from the researcher. So I always needed to check in with the participants. You know, they sometimes the application produced problems, so it required considerate resources. So that was the main reason that we kind of limited this period of data collection. But in general, of course, you're right that, you know, it would be worth collecting more data.
Yeah, but okay, how much do you think this, because the title is stress prediction, is it really that simple?
Yeah.
How much do you think this is connected to predicting the stress, and how much is it connected to the fact that you have this relatively small number of subjects, and everyone is quite different and so on?
Yeah, I mean, the sample is kind of small if you, especially you know, in machine learning community standards. But you know, here we really try to focus on like how stress changes from day to day, and for that 15 working days is kind of okay, I would say, especially comparing this to other diary studies which were similar. And yeah, I can tell you that they usually only collected a couple of days data, or you know, they had a relatively low number of participants. So while the sample is, by the standards of machine learning small, for this type of study is fairly large.
I see. Okay.
Yeah.
May I also ask another question? So I noticed, well, this is not really a question, it's more a suggestion. So I noticed that the results for five-fold cross-validation were pretty decent, which kind of suggests that if you take a lot of data of the subject for whom you're doing the predictions, that, well, the problem becomes well solvable, which is otherwise, unfortunately, not really the case. So I think if you try to do the clustering differently, maybe you could approach this. The clustering, if I understood correctly, was done relatively simply. So you clustered on, I don't know, just a few variables or even just one.
Just one, yeah.
Yeah. But I mean, if you clustered people by their, I don't know, physiological signals, phone usage, everything that's not questionnaire, or a subset of this, maybe you could get significantly improved results. I don't know, maybe it just wouldn't work, but I think this is something worth trying, and whether this can work could even be tested so that, you just experiment with different combinations of users and see if any of them are really good. And if they are, then you can then you can try to figure out how to select them without extensive experimentation. Now you couldn't take all the combinations of users because there are too many, but this kind of experimentation could maybe lead you somewhere.
Yeah, and to comment on why this improves the results so much, I think it has to do with between participant differences. So because participants are so different, the leave one subject out is a very difficult cross-validation technique. As soon as you at least see some of the data, and this was stratified k-fold cross-validation, meaning that for each participant 20% of the data was reserved for testing, then the problem becomes easier. Yeah.
I mean, did you test empirically how this stratification affects results? Because standardization, because you can standardize features, you can standardize class, you can standardize both, you can standardize neither.
Yeah, I haven't done this comparison, but yeah, it's definitely an option.
Okay, I'm sorry, Filipa, I'll shut up now.
No problem.
Yeah, thank you for the questions.
Okay, so we are right on time. I think we can close the session. Thank you, Junoš, again for your presentation. And thank, of course, the audience for your insights and questions. I want to remember you that this seminar will be available on our YouTube channel, on the WideHealth YouTube channel, so you can revisit this seminar and contact Junoš in the future with further questions, more questions that you have. That said, thank you all again, and I hope to see you on our next seminar.
Thank you.